Hello, Sauce here. This lesson is on instantaneous rate of change as a function. We're going to start with a function I'm going to call the p function, and it is a function of time. P for position, t for time. We can imagine that this expression will calculate the position of an arrow in its trajectory through the air, or a car driving down the road, or a rocket taking off. And a typical question to ask, given something like this, is what is the velocity of the object that is guided by this position function at any time t? And in the past, we've done problems where we're given a specific value of t, like what is the position of the arrow at time 3. But in this case, we want something that'll tell us the velocity at any time that we choose. We've been working with this concept, the relationship between position and velocity. This is a physics context. The relationship of position and velocity is the rate of change of position. A car is a machine that changes your position, and the velocity of the car is what you can read while you're driving on the speedometer. How do we take position information and get velocity? We need to take the instantaneous rate of change of position, which is a mathematical process. If we were to take this equation and use the instantaneous rate of change expression on it, what we'd produce is a function for the velocity at any time t. Let's do that. IROC of position is equal to, in general, the limit as h goes to 0. In this case, I'm going to make it in terms of the p function, p t plus h minus p of t all over h. We don't have a specific time t. So when we go through this process, we're going to keep t as the variable. H is it is a variable, but it is involved with the limit. So we're going to keep track of this expression with both t and h in it all the way to the end. Next line of work. I'm going to compose the p function now with t plus h. So that's going to be t plus h all squared, and then add 4. I need to subtract the p of t function, which is t squared plus 4. And of course, I'm in the habit of needing to distribute the negative, so I put the whole function that I'm subtracting inside of parentheses. And I make them brackets so that I can see with my eyes very clearly that I'm going to need to distribute the negative. Good habit. Next line of work, we're still taking the limit as h goes to 0. I'm going to distribute the t plus h all squared, t squared plus 2th plus h squared. Don't forget the plus 4. And I'm subtracting the t squared, and now distributing the negative means I'm going to subtract this 4 as well. Still all over h. I've got some terms that I can combine, and they'll cancel out. T squared and this minus t squared cancel out. This plus 4 and this minus 4 cancel out. What I have left is the limit as h approaches 0 of this term here, 2th, and this term here, h squared, still being divided by h. And notice we should expect that when we process the algebra and the IROC expression, we need to expect to eliminate the division by h problem, because if h is going to 0, it's a problem to divide by 0. The algebra, if done correctly, will always resolve, and in the next step you'll see that this h will divide this h in this term, leaving 2t, and the h squared after it divides by h will just be h, and I'm still taking the limit. The division by h, where h is going to 0 problem, is resolved, and now it's time to take the limit. When I do, h goes to 0, the 2t term doesn't change, and I can simplify this to 2t. What I've calculated, what I've found, is an expression that still has a variable in it. That's because I never had, from the beginning, a value for t to replace t. So this 2t is a function to find the velocity at any time t. This here is equal to the velocity at time t. And that's the prize. Let's use it. Let's imagine that the question now wants us to find the velocity of an object given this position equation at 3 seconds, or time equals 3. So if time equals 3, then the velocity at time 3 will equal 2 times that time, and that's equal to 6. I haven't been given units in this problem, so it's going to be an abstract 6. Now, what does this mean graphically? Let's sketch the situation. The position function t squared plus 4 is a transformed parabola. If I graph a parabola and move it up by 4, the graph must look like this, where this tick mark is at 4. And this curve is the graph of p. What does that have to do with this 6? The velocity at time 3 means that if this is the time axis, and I was looking at 3 in the domain, the tangent line to P, the one that grazes P when time equals 3, this number 6 is the slope of that tangent line. 6 is the rate of change of P at that particular point.